Brahe, Kepler, and then Galileo have made great strides in taking these celestial objects and studying them as physical concepts that we can measure and discuss and hopefully understand. But the real understanding waited a few more decades for, as I promised, Isaac Newton. We're going to spend the next few clips following in the steps, the rather large steps, of Sir Isaac and seeing what it was that he taught us. And we're going to start at the beginning with mechanics, the science of motion, which is going to underlie everything else. So we're going to do some physics, bear with me. It's going to be intense. To study motion, the first thing we need to do is make mathematically precise what it is that Galileo said when he said an object retains its state of motion. So mathematically, the state of motion is represented by an object's velocity. Velocity is a physics concept. It means the speed with which something is moving along with its direction. So we denote it by this V with an arrow on top of it. V stands for velocity, and the arrow reminds us that this is a number, the speed at which something is moving, along with the direction, so that this ball can be moving at 1 meter per second to your left or my left, and at 1 meter per second to my right, or up or down, or in or out. And those, even if the speeds are the same, are different values of the velocity. Velocity can be thought of, as we know, speed is measured in meters per second because it is the change in position, in where you are, the distance divided by time. And velocity can change. The ball can start slowly and speed up. And its change is called the acceleration. So acceleration is the rate at which velocity changes, and acceleration is measured, therefore, in meters per second, the difference in velocity between the beginning and the end of an interval, divided by the length of the interval. The same way that velocity is distance divided by time, acceleration is velocity per time. And so the rate of change of velocity is an acceleration, and it's measured in meters per second squared. And like velocity, acceleration has a direction. So that if an object is moving to the left and speeding up, then its acceleration points to the left. If an object is moving to the left and slowing down, that means its velocity points to the left, but its acceleration points to the right, because the velocity is less to the left later in the interval than it was before. So acceleration, like velocity, has a direction. And in addition to expressing the fact that an object could be speeding up or slowing down, there can be a change of velocity that is associated with maintaining the same speed, but merely changing direction. If an object is moving to the left and starts moving towards the camera, this is a change in velocity even if the speed never changed. And a particularly useful example for us in studying astronomy is going to be, in fact, of motion without changing the speed. Let's look at it, and maybe it'll help clarify these concepts a little bit. The example we're going to want to study is the example of an object, say maybe a planet, moving in a circle about some center, say the sun, at a constant speed. So in this first pane, you see the black dot, which is our object, and it is set so that it is moving around a circle at a constant speed. Its speed is not changing. Its velocity, however, is clearly changing, because if I freeze the animation here, the velocity of the object, manifestly, is pointed in this direction. It's moving that way. Whereas, if I let the animation go a little farther and freeze it again here, the object is moving at the same speed, but in a different direction. And therefore, there is definitely a change in speed, and to quantify and understand that change in speed, we will move down to this pane, where I have put in the object's velocity. It is an object with a direction, so we draw it with an arrow, and the arrow at the beginning points up because that's the direction in which the object is moving, and as the object moves, the velocity changes because while the arrow is of the same length, its direction is continually changing. So this is the way your velocity changes when you move around a circle at constant speed. Coming down here, I've got two circles, the circle along which the object is moving, and then this imaginary circle. And if you look, what the imaginary circle does is I've copied the blue arrow over to here and drawn it so that its tail is always at the origin. So the edge of this arrow is giving me the direction, and of course the constant magnitude constant size of the velocity vector. When the arrow points to the right, the object is here and it's moving to the right, and so on. So this is my velocity vector v. Now I can understand how to measure acceleration. Acceleration is going to be the rate of change of this vector, so that if I freeze the animation at any given point, I can see what's going on. The object is over here, it is moving in this direction. That's why this velocity vector points this way. But I know where the velocity vector is going. It will next move over here to the right, so the vector that measures the change in velocity will point along this circle, just as the vector that measures the change in position points along this circle. To make that clear, here's the same two circles, and on this, here on the velocity circle, I've added a green arrow to represent the change in velocity. And as they play, you see that as the green arrow is constant in magnitude because the velocity is rotating at a constant rate, just because this thing is rotating at a constant rate. And the green arrow points along the velocity circle. And what this green arrow is, in fact, is our acceleration. It's the rate of change of the velocity. And so to make that explicit, I've here done 3 circles. This is the position circle, this is the velocity circle, and over here we have the acceleration circle, where I've taken the green arrow, the rate of change of velocity, and moved its tail to the center, so that at any time this gives me the rate at which the velocity is changing. So you can play with all 3 arrows, and I'll post this file so you can try to run it. The main thing I want you to notice here is that if you look, there's a relation between the directions of the acceleration arrow and of the position arrow. When the position arrow points here to the upper left, the acceleration is to the bottom right, and that's not a coincidence. Velocity is 90 degrees to position. Acceleration is 90 degrees to velocity, adding up to 180 degrees away from position. So when you're out here, your acceleration points that way, and if I move it and freeze it again, you'll see that this is always maintained. When you're at this position, your acceleration points in that position. So the acceleration at any given point is in fact, at any given time, is in fact pointing directly to the center of the circle. If you ask, in which direction is this object moving? It's moving along the circle. In what direction is it accelerating? That way, towards the center. So we found that moving in circular motion at a uniform speed, you're experiencing an acceleration of constant magnitude, always directed towards the center of the circle. Now, if it's important for us to understand this circular example better, so let's go through it. If the radius is r and the speed v, I want to know, we know the direction of your acceleration. What is its magnitude in meters per second squared? So I'm looking for an acceleration in meters per second squared, and it needs to be determined by, what is there to determine? The fact that you're moving around a circle of a given radius at a given speed, and we all have an intuition that if you're going faster around a curve, you'll need to accelerate more to take the curve. And if the curve is a tight curve, you need more of an acceleration. So let's see if this is borne out, and we'll use a trick that physicists use. It comes from units. We're going to do what we call dimensional analysis. We need to find some combination of r and of v that could, in principle, be an acceleration. And it turns out there's only one. Because if you think about it, r is measured in meters. It's a length. V, being a velocity or a speed, is measured in meters per second. We need to fashion out of these something that could potentially equal a. And it's clear that the only way we're going to get seconds squared in here is to take the square of the velocity. So write the square of the velocity. This is a good idea, but that has units of meters squared per second squared, because it's the product of 2 things with units meters per second. So that's not quite right. This does not have the right dimensions, but we need to clean out the meters, and to clean out the meters, we can simply divide by r, which is measured in meters. Now, dimensional analysis doesn't always give the exactly right answer. If the acceleration could easily have turned out to be 3 pi times v squared over r, and the 3 pi would not show up in dimensional analysis. In the case at hand, it turns out that there is no constant. You can do the calculation. It takes a little bit of effort, but we're not going to do it. The answer is that we got the right answer. For precise, correct expression, using just this dimensional analysis. So the acceleration towards the center of a circle is given by v squared over r. It has the fancy name centripetal acceleration because it is towards the center. And this will show up often in what comes next. We now have a nice way to state Galileo's principle of inertia. An object upon which no external influence acts moves with constant velocity, or equivalently, has zero acceleration. Now we step it up. What happens when an external influence acts? And Newton introduces a brilliant concept here, which is the external influence is quantified by something called a force. What is a force? It's a tricky concept. A force is that which causes acceleration. The idea that Newton introduces is that you can imagine applying the same force to two different objects. And we all have that intuitive idea. I can give an identical push to a tennis ball and to a refrigerator. And we all have the intuitive idea that we'll get more of a motion out of the tennis ball than we will of the refrigerator, because the refrigerator is heavier, or technically the refrigerator has a larger mass. And so Newton quantifies this intuition in the idea that there is such a thing as a force, something that measures the amount of external influence being applied to an object, and the object's acceleration is related to this force by a property of the object itself known as its mass. And the mass is roughly the amount of stuff in the object, all counted, weighted appropriately. It's measured in kilograms, and an object that is massive is an object that is heavier. We'll make that precise in a second. And force, like acceleration, has a direction. You can push something to the left or push it to the right. And so we have this new physical concept of force. We need to understand what units we measure force in, and that follows directly from this equation. A force of 1 unit is a force that causes a mass of 1 kilo to accelerate at 1 meter per second squared. So the unit of force is this unit, kilogram times meter per second squared, and it is dignified, of course, with the name Newton, and denoted by an N, so that would be a force of 1N. Before we go on to clarify some details here, let's go on to Newton's third law. This was Newton's second law. And Newton's third law explains why there has to be an external agent applying the force. And this is crucial. Newton tells us that universally, when an object A is applying a force to B, and the force is given by F, which means B is being accelerated, something is applying the force, go find the thing that is applying the force, then B automatically reacts on A, we call it, and that means B applies to A force that is equal in magnitude and opposite in direction. We write it mathematically as negative F. Negative, a vector, means a vector of the same size pointing in the opposite direction. What this means is that when you push on the refrigerator pushes back on you. This is not an action by the refrigerator. This is not some act of will. It's Newton's third law in action. Now, let's do an example of this. It was known already to Galileo that if we let loose some object, we all know this, if I let something go, this ball right here, then an external force will act on it. How do I know? Because the ball has an initial velocity of 0, and clearly it does not maintain the initial velocity of 0. It begins to move downward, so it has a downward pointing acceleration. And in fact, this acceleration was measured by Galileo and people after him, and it has the interesting property that it is uniform for all objects. So any object in the vicinity of Earth accelerates down. The acceleration is called the acceleration of gravity, and in our fancy units, it's about 9.8 meters per second squared. This is my son's 10-kilo shot put ball. And when I hold this, I'm preventing it from falling down with the standard acceleration of gravity by applying a force directed upwards to the ball. Newton's third law then tells us that if I'm applying a force to the ball, directed upwards, then the ball is clearly applying a force to my hand, directed down, and believe me, I can feel it. Of course, gravity is going to play an important role in what goes on. It's also a force that acts all around us, so let's quantify what we said. The weight of an object is defined to be the force gravity applies to it. We know that objects on Earth fall with an acceleration that I told you, 9.82 meters per second squared. So the force of gravity on any object is directed always down. It's given by the mass of the object times this constant, which is why we confuse mass with weight, but separate the two. M is a property of the object. G is a property of Earth. We often say that I weigh 59 kilos. A more correct statement is that my mass is 59 kilos. My weight here on Earth is mg, which is 59 kilos times 9.82 meter per second squared, or, doing the calculation, I believe I did it right, 579 kilos times meter per second squared, which is 579 newtons. My weight is 579 newtons. We'll play more with the specifics of Newton's laws, but the first thing we need is to understand some very deep and important consequences that are mathematically derived, and Newton derived them, from Newton's laws. And the most important of these take the form of things called conservation laws. There are quantities that you can define for a physical system that do not change. So let's look at this. And the first conservation law involves this quantity called momentum. We define another vector called momentum. It's essentially the velocity vector, but multiplied by mass. So roughly it measures the amount of oomph, the amount of inertia, some people say, that the object has. A refrigerator moving at 2 meters per second has more momentum than a tennis ball moving at 2 meters per second. The reason this is important is because F, being satisfying Newton's law, let me rewrite it again here, Newton's second law, F is mass times the rate of change of velocity. Since mass does not change, it's a property of the object, F could be thought of as the rate of change of this momentum thingy. And so if F is the rate of change of momentum, we have something very deep. Imagine that there are only two objects in the universe, but there are forces between them. So A acts on B, and the velocity of B changes, and B acts on A, and the velocity of A changes. What we know, though, is that the force that A applies to B, whatever it is equal in magnitude and opposite in direction to the force that B applies to A, which means the rate of change of A's momentum is equal in magnitude and opposite in direction to the rate of change of B's momentum, with the consequence that the rate of change of the total momentum, add up these two vector objects, the total momentum cannot change. Now add more objects, and the same principle extends. There is in the universe a total conserved object, the total momentum of the universe, and that cannot change. Moreover, if you get to isolate some subset of the universe so that it doesn't interact, there are no external forces on it, then the momentum of that little group of objects is completely conserved. All that forces can do is allow objects to exchange some momentum. Some momentum can be transferred from one object to the other, so the momenta of the two objects change, but the total is unchanged, and we say that momentum is conserved. We call this a conservation law, and such conservation laws are critically important. Let's take a look at what this looks like. This is a toy, appropriately enough, called Newton's cradle. It has a row of 5 steel balls hanging from a framework, and we will pull one ball off to our left so that when I release it, it will impact the row of balls with a horizontal momentum pointing to the right, and let's see what happens. What happens is that the incoming ball comes to a complete halt, transferring all of its horizontal momentum to the next ball down the line, which transfers it to the next, and so on, until the last one leaves the pile with essentially the same momentum as the one with which the initial ball came in. We can repeat the same process with 2 balls and see a similar interesting process. We can do 3, and if we are ambitious, even 4 balls, and reproduce the same results. I hope I convinced you that we can see mathematically where Newton's laws lead to momentum conservation very directly. A little more math that we're not going to follow through shows that there's another way to find a conserved quantity that is associated deeply with circular motion. So it involves picking a center for motion. And it's called angular momentum because circles are parameterized by angles. And it's a quantity that is given, it's related to momentum. Here's our friend momentum. But it's the momentum times the radius of a circle in which one moves. And what one finds is if you have a collection of objects that are all moving together, you sum up, just as with momentum, the total angular momentum, the mass of each of them, times the velocity of each of them, times the radius at which each of them is moving around the circle. This is assuming everybody's moving in a circle. There are more complicated expressions in other cases. Then this angular momentum is also conserved in that it can be traded between different parts of a system, but the total is conserved. This is going to be extremely important to us because things in space tend to spin, so let's demonstrate that with our valiant demonstrator. Standing on a platform and holding out some weights, I have my friend Derek start me spinning slowly, and what we see is that as I pull the weights in, they have a significant factor of m, and I'm making their r smaller. My angular momentum is conserved by making all of me spin faster, and I can control my speed. When I pull my arms out, I slow down. When I pull them in, I speed up again. This is a great demonstration of the conservation of angular momentum, if not perhaps of exceptional physical grace. There's another conservation law that you can show follows from Newton's equations. Imagine an object upon which the only force that acts is gravity, like this rubber ball when I throw it up and down. So as long as the ball is in the air, essentially gravity is the only force acting. And what we know is that when I throw it, as it moves up, it'll slow down, and then as it comes down, it'll accelerate, moving down. This is formalized in the following statement. It turns out that if you form the combination m times g times h, where m times g is the force that gravity applies, and h is the height of the object above something, my hand, the thrower, it doesn't really matter what, we'll show why. And if you take this quantity, which we call gravitational potential energy, and add to it this combination of speed and mass, m times v squared over 2, this combination is called the object's kinetic energy, then the sum of both of these is constant. As h increases, the object slows down, because that's how gravity works, and as it falls down, it speeds up, and this mathematically expresses this. Notice that it's clear from here why I could have measured the height from the floor, or my hand, or the bottom floor of the building. It doesn't matter. That just adds a constant that never changes. So adding a constant to the energy until very late in this class will be completely irrelevant. Now, this is very nice, but it's only true if the only force acting is gravity, and in general there are other forces that act. And so in general, this conservation of energy is violated. But not really. What really goes on is that whenever there is another force other than gravity acting, a typical example is friction. If I roll my chair back, it slows down. It had kinetic energy, and the energy disappeared. Where did the energy go to? Well, if you listened closely, you could have heard that some of it turned into sound energy. It's also true that there is friction in the bearings of the wheels, and that converts some of the energy to heat. Heat is a form of energy, and friction is a force that converts kinetic energy very happily into heat. So there are many different forms of energy: sound, light, heat, chemical energy, electric energy, nuclear energy. We will talk about all of them in turn. They'll all show up. When you add them all up together, it turns out, in any process, the total energy in the universe is conserved. And again, if you isolate a chunk of the universe from the rest, then the total energy in that chunk is conserved. Energy is neither produced nor destroyed. This might come as a surprise to all the politicians who talk about the need to produce energy or conserve energy. Both of those are political terms, but scientifically, energy can neither be produced nor destroyed, and it can be conserved. In fact, it always is. It's a very important concept to us. Let's remember the units in which we measure energy. So they follow from this equation. Energy is measured in units of kilogram times meter squared per second squared. If you plug it in, you'll see that both of these terms have the same units, which is good because otherwise adding them up would make no sense. And this is dignified by the name joule and indicated by a J. So this is joule. And it's hard to have exactly a sense for how much a joule is. So let me help you by perhaps suggesting the following idea. Our body, to push this chair back and forth, to move my arms, I'm producing kinetic energy by converting chemical energy from the food I ate. And we measure the energy content of food in calories. We all have some sense of what a calorie is. So 1 joule is about 4.2 calories. Fun demo of conservation of energy is this bowling ball pendulum. I'm holding it up against my face. It's got potential energy because the angle elevates it from the floor. I release it. It acquires potential energy, swinging it to the other side, converting it back to potential. And when it comes back, if energy is conserved, it will not go any higher than it did before, and therefore will not smash my face. Let's try it. This is it. Those are Newton's laws. I don't know if you appreciate what I mean by this is it, but by the end of this class, I think you'll have a deep understanding of this. In a very real sense, this is all of science. Certainly all of physical science. The equation that governs science is F equals ma. The rest of certainly a century of physics is figuring out the details in the sense of figuring out m, what kind of objects are in the universe, what do forces act on, and figuring out f, what are the forces between various objects. One way I want you to think about this equation, fancy name is a differential equation, but what this really means is it's a prescription for figuring out what the universe will do next at any given moment. And the way it works is this. If we know the forces that act on things, and we happen to know at some instant where all of the relevant objects in our system are, and because this only determines the acceleration, we need to know how they're moving, because if a ball is here, clearly there are several different motions it can do under the influence of gravity. It could just fall, or if it is initially moving up, it'll go up and then go down. But once you know where it is to begin with and which way it's moving, then gravity takes over and tells you the rest. In other words, you can take the positions and velocities at a given instant, use those to figure out what the forces are. Perhaps where it is might influence what forces act. Is it touching my hand? Is it not touching my hand? That allows you to figure out the accelerations. Those tell you in turn how the velocities will change, so you can figure out the velocities an instant later. Using those velocities, you can now figure out the new positions, figure out the new forces, and repeat. This process is called solving a differential equation. And in essence, what the universe does is it solves Newton's equation all the time. What this allows you to do is if you have some knowledge of what we call the initial data, all of the positions and velocities of the parts of your system at any given instant, you can predict what everything is going to do into the infinite future, and also you can roll the clock backwards and figure out where everything was at any given time all the way into the indefinite past. And as I said, most of a century of physics goes into filling in the details of F and M and applying Newton's laws in various situations and finding the consequences. Let's start that process with the force that's most important to us, which is gravity, in the next clip.